The University of KwaZulu-Natal's College of Agriculture, Engineering and Science is committed to making a difference in our world, from the classroom and laboratory to the field. It provides one of the finest study and research environments on the African continent and is recognized internationally as a center of excellence. Agriculture, Engineering and Science is one of 4 colleges that make up the University of KwaZulu-Natal and is home to over 8,700 students and approximately 700 staff. 3 of the university's 5 campuses form the core of agriculture, engineering and science activities in the region. The college comprises 5 schools: agricultural, earth and environmental sciences, engineering, chemistry and physics, life sciences and mathematics, statistics and computer science. Engineering is offered on the Howard College campus, agriculture on the Pietermaritzburg, and all the other sciences on both the Pietermaritzburg and Westville campuses. Exceptions are agricultural engineering, which is offered in Pietermaritzburg, and geology, which is offered at Westville only. To compete with the best and to meet the challenges of the 21st century, South Africa needs highly skilled professionals in the areas of agriculture, engineering and science. We offer a wide array of interesting and innovative degree programs that open doors to a variety of different careers. Some degrees are unique to UKZN and are not offered at other tertiary institutions. For example, we are the only university in South Africa to offer a fully accredited agricultural engineering degree and one of only 2 universities in the country to offer a BSc in land surveying. Our postgraduate food security training program is the only one in the world, and we have the widest range of agricultural disciplines at any single South African or African campus. The choices of degree and the options on offer may seem confusing at first. Engineering degrees are more specific, and the options are usually career-focused. Emphasis is placed on training in the specific principles which engineers deal with in their professions. Engineering offers 7 different professional specializations. There are also degrees in land surveying or geomatics and property development. In science, there are structured or career-focused degrees. These include fields as varied as chemical technology, marine biology, industrial and applied biotechnology, and computer science and information technology, to mention a few. There are also more general degrees with a lot of flexibility. In this case, students have the choice of studying a BSc M stream in maths, physics, computer science, and statistics. All of these have a strong mathematical component. The other option is a BSc LES stream with a focus on the life and environmental sciences with subjects such as geography, genetics, botany, hydrology, zoology, ecology, and microbiology. In agriculture, there are various different options that involve practical and scientific applications. Students can combine science subjects with specific agricultural disciplines for a 4-year Bachelor of Science in Agriculture degree. These are more career-orientated. Agriculture and agricultural management are 3-year degrees with a higher practical component. Dietetics is a professional qualification that deals with the role nutrition plays in the promotion of health and the treatment of disease. Most degree programs across the college have field trips and projects that contribute significantly to the curriculum. This ensures that students learn in real-life situations under full field conditions. Many of our lecturers have received Excellence in Teaching awards, are recognized internationally, and are rich in practical experience. Students have access to excellent facilities that rank amongst the best in the world. 300 million rands has recently been invested in new teaching and research facilities, state-of-the-art laboratories, and improved equipment. The 30 million rands new School of Engineering building is the envy of engineering campuses across the country. Agricultural students have access to a 356-hectare research and training farm situated near the Pietermaritzburg campus. This facility provides students with hands-on training and is used extensively as an outdoor laboratory for teaching and research in areas such as animal and poultry science, horticultural science, and agricultural engineering. Adjoining Ukulinga is the Bisley Valley Nature Reserve, which supports a diversity of plant and bird species, as well as some large mammals. It provides a rich learning and research environment for staff and students. Based on the Westville campus, the college possesses unique facilities for research into higher voltage power transmission. These facilities are available in only 3 other places in the world and form part of the ESCOM-sponsored Science and Technology Innovation Park. The Science and Technology Education Center showcases the college's scientific achievements and promotes the public understanding of science, engineering, and technology within the region. The college houses a wide range of sophisticated equipment in its microscopy and microanalysis units, staffed by highly qualified and skilled technical specialists. The College of Agriculture, Engineering, and Science prides itself on its graduates who are highly sought after. In a market characterized by a shortage of qualified professionals in science and technology, our graduates are readily employed around the world in the fields of agriculture, science, commerce, industry, engineering, and research, to name just a few. Research plays a major role within the college and operates at the cutting edge of technology. College has the highest research output in the university and produces the most research publications. There are over 60 well-established research groups and centers within the college. The African Center for Crop Improvement caters for students from all over Africa. It is one of only 2 African plant breeding programs on the continent. Based in the School of Agricultural, Earth and Environmental Sciences, the African Center for Food Security focuses on alleviating hunger in Africa. It offers food security training programs, undertakes academic and applied research, and provides policy and program support. Promoting sustainable engineering practice is the Center for Research in Environmental, Coastal and Hydrological Engineering, or CRESH. It deals with the interaction between engineering and the natural environment. The Mechatronics and Robotics Research Group in the School of Engineering provides an excellent research and education environment for its senior undergraduate and postgraduate students. Judged one of the best research centers at the university, the Center for Plant Growth and Development focuses on high-quality research in the plant-based disciplines of plant physiology, plant molecular biology, and ethnobotany. The Center for Quantum Technology deals with physical phenomena at the microscopic level. Quantum physics led to the development of the transistor and the laser, and is currently being used to develop quantum computers and quantum cryptography. The college is committed to access and readdressing the disadvantages and inequities of the past. The highly successful Unite Engineering program and the Science Access Foundation and augmented programs offer alternative access to university, equipping students from disadvantaged backgrounds with the skills and knowledge to pursue their degrees of choice. Both these programs contribute significantly to advancing Black African scientists and engineers in South Africa. Staff and students contribute to a number of outreach and community initiatives that focus on social responsibility, sustainable development and upliftment of the wider community. The college also engages in activities involving the pursuit and understanding of science, engineering and technology through exhibitions, festivals and roadshows that target high school learners and the general public. The college has minimum entry requirements for its programs. These differ from degree to degree, but all require a national senior certificate and minimum performance levels in mathematics and either physical or life or agricultural sciences. For those who do not meet the minimum requirements, access programs are available. Additional information and brochures can be obtained from the contact information accompanying this video. The College of Agriculture, Engineering and Science is proud of its contribution to the university, the region and the country.
UKZN is one of the best. I definitely understand it's one of the best in South Africa. So for me, there was no other institute that I would have preferred other than UKZN.
We have the best facilities here in terms of laboratories, in terms of equipment, in terms of human resources, in terms of literature.
UKZN is one of the best universities in the country that teach agriculture or natural sciences.
What I think is good about this college is the level of international collaboration that we have. We have friendships with universities all over the world, which means that we're keeping up to a great international standard.
UKZN has got much more facilities and it's recommended worldwide to do your science studies here. Life begins here. Yes.
We continually strive to be academically excellent, innovative in research, and critically engaged with society. We invite you to join us or work with us to be part of this exciting team.
What? Hi, good evening, Ashwin.
Hi, good evening, Dr. Bissessur. How are you?
I'm good, man. We've been just having some hectic weather, and I think the load shedding and connectivity problems is just adding to our woes. But in any
It's
case,
the same here.
yeah. So, do we have some? I see we do have some students on board to listen to today.
Yeah, we're also recording, so this can be used long term for future revision.
Okay, I'm gonna do the electrochem, and the other section was stoichiometry. I can go through some stoichiometry with them, which will be helpful in some of the calculations.
Okay.
All right, I'll kick off with the electrochem, and then I'll take it from there.
Okay, thank you.
If by any chance that the lights go off or if it buffers, then students just stay on, because then we'll try and okay. So yeah. So what we'll do is we'll stay on, and then we'll just see if we can get back online. But let's take it from there and see how we go. All right. Right. Good afternoon, students. Hope you guys are doing well. If you can hear me, could you just give me a thumbs up? Great. Right. Today is ideal weather. We're going through some quite hectic weather patterns. They say it's due to global warming, and obviously you know what the effects of global warming is. All our poor practices, many of the so you can see my background picture is the Louvre in Paris. I don't know if anybody's been there. Anybody's been to the Louvre in Paris?
Oh.
No. Okay. All right. If you got a chance and if you got some money, you can get to the Louvre in Paris. I'm trying to comb my hair, but everything is not going right. All right. So if you get to the Louvre in Paris, it's actually a very nice place. And why I put this picture up, because the Paris Agreement of 2010 basically took place after the Kyoto Protocol. Sorry, the Paris meeting of 2019. The Kyoto Protocol, I think, was in 2010, and there all the countries got together and signed the treaty to reduce emissions, carbon dioxide emissions. So all the countries are trying to reduce their carbon dioxide emissions, and this was a treaty that was signed in Paris. And so, talking about weather changes, global warming, etc. Our country, South Africa, there seems to be no control over emissions, over waste management, recycling. You saw, and I'm sure many of you are getting quite a lot of information on WhatsApp to see all the roads. And my whole point here comes to all of this, what I'm telling you, comes to a certain point in time, in a few minutes. But you saw all the infrastructures are starting to degrade in South Africa. That means when it rains, all our drainage systems seems to collapse. Roads seem to have sinkholes. Why are these situations or scenarios happening? That's obviously because of non-maintenance. And this actually comes down to science, to materials, chemistry, physics, mechanical engineering, chemical engineering, and all of these different aspects that comes together to make a system work. So you guys are here, trying to get an education, but where do we put it forward? And all the things that we learn, let's try and put it into something tangible that can help us first. So I think that's the important aspect. Right. One of the systems that we look at is acidic systems, and you find that a lot of redox reactions take place in these drainage systems. Right. You have microbial degradation, oxidation reduction taking place. Also, when you have different systems that are present, we can have redox reactions taking place. I'm going to now share my screen. So my topic for today is basically where can I find those notes? No, I can't find those notes right now. Just give me a few minutes and then I'll share that screen with you. Okay. Okay. Let's see if I can get it now. Right. Okay, so we're going to look at electrochemistry. I know you can score quite a lot of marks in this particular section. When you learn a section, it's not about going and saying, if you take your notes and you say electrochemistry is the study of relationship between chemical change and electrical energy, by hearting these things and trying to just study it for the sake of writing an exam and getting a mark is not going to help. In chemistry, in science, in engineering, you've got to understand a concept very, very effectively. All right. It's very important for okay, I think someone has got their mics unmuted. If they could just probably mute. Okay, unless it's just some feedback that I'm getting. So when I'm going to explain stuff to you on electrochemistry, right? You must have a very good understanding of the concepts, and then you can work out the problem. So I'll go through some of the problems and show you how easy it is to basically work out all these electrochemistry information. And what does it mean? How does it help us? Okay. So electrochemistry is the study of the relationship between chemical change and electrical energy. So what does that mean? It means there's a chemical reaction taking place, and then there's an electrical energy that's produced. I can still get feedback. Can all of you please mute your Can I ask all of you to please mute your mics? Thank you. I'm just trying to find the person that's unmuted.
Everyone's muted now.
Okay. All right. Thanks, Ashwin. Maybe it was just feedback on my side. Right. So thermodynamic principles explain how cells work. Thermodynamic principles explain how cells work. That means we're going to use thermodynamics to explain an electrochemical process, because electrochemical processes absorb energy or they release energy, right? So I said to you, when we look at electrochemistry, we're going to look at a chemical reaction, and born out of that chemical reaction, we're going to release energy or we're going to absorb energy. So this kind of energy in electrochemistry involves movement of electrons from one chemical species to another. And you are familiar with this redox reactions. So the reaction that's going to take place is a redox reaction. We're going to get a flow of electrons, and that's now going to generate a type of energy that we get out of it. So let's review some redox terminology, and I want you to be very, very confident about this. Confident mean you don't, if you're looking at a species and you look at a change in oxidation number, you're not going to think twice as to what these things mean. So a redox reaction involves a change in oxidation number. So what is oxidation number, right? So obviously, let's look at the simplest, group 1, sodium. And if sodium loses an electron, it goes from Na, which is a neutral atom, to Na+. So you can see it's an increase in oxidation number from 0, because any neutral atom on the periodic table has got a 0 oxidation state. And when it becomes plus, so we don't write it as +1, we just write it as plus. So it becomes +1, which means there's an increase in oxidation now. Right. So oxidation, as you know, is the loss of electrons, and reductions reduction means the gain of electrons. Okay. So what is an oxidizing agent? Obviously causes the oxidation of another by accepting an electron from it. I'll show you an example just now, and I'll clear up these definitions. And what is a reducing agent? A reducing agent causes reduction by giving an electron. So for example, I told you sodium, if it gives off that electron, it is the reducing agent because it's giving an electron to another species, and that species takes that electron, so it becomes the oxidizing agent, right? So something that a species that gets oxidized is a reducing agent, and a species that gets reduced is the oxidizing agent. So you'll see I've got a little note at the bottom saying reduction oxidation always occurs in pairs, and the number of electrons gained by the oxidizing agent equals the number lost by the reducing agent. Okay. So let's look at an example. And here's a typical example, right? So sometimes when we learn about words, it's best shown by an example. So what is being oxidized and what is being reduced in the following? Now you've got to learn how to remember oxidation numbers of different atoms in a molecule. So if you look in this example, cadmium, so whenever we see something in its stable state, and when we see it, for example, cadmium as a metal, it's in a zero oxidation state, right? So cadmium in its zero oxidation state, and here we have nickel oxide. Now I use the word oxide. So whenever you see oxygen, oxygen has a -2 oxidation state, right? So because I've got two oxygens, the oxidation state above for the oxygen is -4, right? And here the nickel is +4. So you got NiO2, right? Now, water, generally, we don't look at water as being an oxidized species, but it can undergo oxidation under very specialized condition. But what has happened to the cadmium now? So you know hydroxide is -1. And because we got two hydroxides, the oxidation state for the hydroxide is -2, so the cadmium is +2. So cadmium went from 0 to +2. That means cadmium got oxidized. So it is the reducing agent. Nickel went from, so here let's look at the nickel. Nickel is +2 on the right hand side because again I've got two hydroxy groups, which is -2. Each OH is a -1. So I've got an overall of -2. That means the nickel is +2. So nickel went from +4 in nickel or NiO2 to +2. So +4 gained 2 electrons that cadmium gave off and became +2, right? So you can see how we can work out changes in oxidation numbers. Okay, so my advice to you is don't worry about water if it's in a reaction, right? Work with the main reacting species like you see here in this example. Okay, so what is being oxidized and what is being reduced? So when you get a question on electrochemistry, the first thing to do is look at the overall equation. Look at it, identify which species is being oxidized, which is being reduced, and then you can write down the two half reactions, right? But let me give you an overall idea about voltaic cells and electrochemical cells, and then I'll show you how we can work out to calculate, do calculations based on the energy or the EMF, the electromotive force as you know it. So there are two types of cells that we use in electrochemistry. One is a voltaic cell or a galvanic cell, and you must have heard in your teacher must have used the word, an example of a voltaic or a galvanic cell is a Daniell cell. And it uses a spontaneous reaction, right? I'm not too sure if you're familiar with delta G, which is the free energy to generate electrical energy. But what you should just know is that for example, your batteries that you use for your cell phones, right, is a lithium-ion battery. That is an example of a voltaic cell or a galvanic cell. And it produces a spontaneous reaction, and it gives off about it gives off about 3.7 volts, okay, of EMF. So you can basically use your cell phone. So that's a voltaic cell. An electrolytic cell, on the other hand, if you connect an electrolytic cell, it doesn't work. So you've got to give it energy for it to work. And so for example, in the electroplating industry, right, there's an example of an electrolytic cell. So that's a non-spontaneous reaction, meaning that for that reaction to take place, you have to provide energy. But in a voltaic cell, as soon as you complete the circuit in a voltaic cell, that chemical reaction starts to let electrons flow from the anode to the cathode. Okay, so those are the two types of cells. Happy? You understand that? Good. Let's move on. And here's an example and a nice picture of it. So this is an example of a galvanic cell. And this is the typical Daniel cell that you see. Okay. So you have two electrodes. So you can see the shiny copper that's connected to the red. And I'll tell you why we connect it to the red and why we connect it to the black. Right? But in any case, you can have two black wires, you'll still get a reading of 1 point. But just for us to show you, the positive electrode and the negative electrode, we're just using some colors. And this little device here is called a potentiostat. It measures the voltage of the electrons flowing across. So two electrodes conduct electricity between the cell and the surroundings are dipped into an electrolyte. Now, in the previous lectures, you must have heard about strong electrolytes and weak electrolytes. Strong electrolytes, for example, all strong acids are strong electrolytes. They completely dissociate, right? And so basically it's a mixture of ions. So in the blue solution, we will have some copper 2+ and sulfate. So copper sulfate, or maybe some sodium sulfate, but here it's actually copper sulfate. And here in the colorless solution, we have some zinc sulfate. So to set up a voltaic cell is very easy. Here we have a zinc anode. So the shiny metallic lustrous where the black cord is connected to, that's a zinc, a piece of zinc metal. The shiny brownish copper metal that you're seeing obviously is the copper, and that's connected to the red. And then you can see we have a salt bridge here, which means the two solutions are connected, right? So you can see the blue and the colorless. Now, oxidation takes place at the anode and reduction takes place at the cathode. But how do we know that, right? So for a voltaic cell and a galvanic cell to be set up, your reading must always be positive. So you can see on the potentiostat here, we got a 1.1. That reading is telling us that this reaction is taking. So as soon as we complete the circuit, right, that means you can see we connected the zinc electrode to the copper electrode by the wires that we have, right, in the external circuit. And as soon as, because the salt bridge is connecting the two here, and as soon as you connected it, electrons are moving in the black cord and it's moving to the copper, and the electrons are now migrating or transferring to the copper electrode. So this copper electrode now has got a lot of electrons around it. The zinc now is basically oxidizing. So it's going from Zn. Let me see if there's there's it. Oh, okay. Let me just show you the reactions. Let me show you the overall reaction here. So you can see the overall reaction for that reaction is, for that electrochemical cell is Zn, right, goes to Zn2+, and copper 2+ becomes reduced. So I'm just going to go back to that cell now, and I want to show you the picture nicely. So the zinc now is oxidizing. And if you leave it for over a period of time, and if we got enough electrolyte, the zinc is actually going to dissolve. That means all the zinc metal will dissolve, right? And then the copper 2+ will start plating on the copper electrode here. So you can see the oxidation is taking place from the zinc, and the copper is undergoing reduction. So we call the oxidation the anode, and we call the reduction the cathode. So I'll tell you how to remember this. All you have to remember is RHE, right-hand electrode, LHE, left-hand electrode. So Ca, cathode, you remember? At the cathode reduction, Ca, and anode, oxidation, right? So all you have to remember LHE, RHE, and remember Ca, cathode, reduction. Right, so you've seen a picture of an electrochemical cell. Now let's see how we can write down the two half reactions and how we can see what's happening. So, will it always be like that? You want to unmute and just clarify, what do you mean, will it always be like that? What will always be like that?
The left hand and the right hand thing.
Yes.
Will it always be left hand and right hand, like how you said?
That's correct. The physical setup will always be like that. The reduction or the cathode will always be on the right hand side, and the zinc. Okay, we're just doing it. In other words, if you switch it the other way, it'll still be the same, if you understand what I'm saying. But as a general rule, right, it'll always be like that. Right hand electrode is the cathode, left hand is the anode. But remember, this is now only for the voltaic cell. When we come to the electrolytic cell, it's switched, the roles are reversed. I'll explain that to you just now, okay? But just remember, this is the important electrochemical cell to remember. Right, now we said reaction with zinc metal with the copper solution, electrons are transferred, but the system does not generate electrical energy. Oxidizing reagent and reducing reagent are in physical contact. If half reactions are physically separated and connected by an external circuit, electrons are transferred by traveling through the circuit, producing an electric current. Separation of half cells is key to a voltaic cell, right? That's what we're saying here. If we separate them by a salt bridge, if we dip these two into a same solution, that's what the electrons are transferred, the reaction of zinc metal with a copper solution, right? Electrons are transferred, but the system does not generate electrical energy. That means if we take a zinc plate and add it to the copper solution, you won't have electrons being transferred. So we have to separate them by a salt bridge, and we have to connect them by an external circuit so electrons have to move. That's when we'll generate an electrical current. That's when we'll generate an. So we can remove this potentiostat and put a bulb there, right? The bulb will light up. Or we can put a fan. The fan will work. You see, that's the electrical energy that we are generating. You can connect your cell phone and your cell phone will work. You see that? I'm just giving you like a crude example of what it's doing. Right, now, I want you to look at this picture so you can see this picture very carefully. Right, look at this picture. There's the zinc strip. Can you see the zinc strip? Right? Now, just say we put zinc in there and we put copper over there. So oxidation is the anode. The zinc bar immersed in the zinc 2 electrolyte, and zinc bar conducts release electrons out of its half cell. So as the Zn goes to Zn2 plus, the electrons has to travel somewhere, right? So the electron, so this is electron rich, the zinc, right? And what happens is that you can see when we connect the circuit here on the right hand side, can you see the electrons now are moving across to the copper cathode? I'll explain to you now why it moves from the zinc to the copper. I'll explain to you just now so all you have to know now that electrons move from the anode to the cathode compartment, and there must be a connection of the electrical circuit. Okay, so now notice what's happening as well in this electrochemical cell. The Zn2 plus is filling up here, so we got a lot of plus charges. So you can see the role of the salt bridge. The negative ions migrate here to maintain charge balance, and the K plus goes this side, because what is happening? the copper from the solution is now depositing onto the copper metal here, because remember the electrons went from the zinc to the copper. So now the electrons are collecting here, and copper is saying, hey, I need electrons for me to precipitate. So you'll find the copper deposits on the copper plate. And what is happening? So the copper plate gets bigger because you got deposits, and the zinc anode starts to diminish in size because it is actually corroding. So it's actually corroding. We call it corrosion, by the way. Right. So you can see the picture. The first picture here on the left hand side is just showing you the two anode and cathode. And the second picture is showing you when we complete the circuit and you connect a light bulb, it will glow. So there we go. We've got this chemical reaction giving rise to electrical energy, right? So now you understand what's a voltaic cell, and this is also a galvanic cell. And this particular example is called the Daniel cell, right? So oxidation, and you can see Zn2 plus is dipping in ZnSO4, and the reduction is taking place where the copper 2 plus gets reduced on the plate because the copper metal here is electron rich. So the electrode charges are determined by source of electrons and direction of electron flow. So in any voltaic cell, the anode is negative and the cathode is positive. So you can see why it's negative, because as the cathode becomes, as the zinc oxidation takes place, it's electron rich. Can you see that? It's electron rich. And on this side, but when we, and as soon as we link the two with an electrical contact, the electrons flows from an electron rich part to an electron deficient part, right? So that's why we say it uses a spontaneous reaction to generate electrical energy, right? So here is the overall reaction, and you can see zinc got oxidized to Zn2 plus, and the copper is getting reduced to copper solid. So LHS, RHS, oxidation, reduction. LHS is the anode and RHS is the cathode. Now you know why I've explained why they are negatively charged and why the RHS is positively charged. The mass of the Zn rod decreases because it's obviously undergoing oxidation, like you can see in the picture now. And the mass of the copper is increasing. You can see that. The mass of the copper rod increases because the copper is depositing. So concentration of Zn2 plus increases and the copper 2 plus in solution decreases. Here are the half reactions. At the anode, the zinc undergoes oxidation, and at the cathode, the copper undergoes reduction. So you have a oxidation half reaction and a reduction half reaction. So in your exams, if they ask you to write the oxidation half reactions, now you know how to do it. Obviously, we have 2 electrons because you can see Zn goes to Zn2 plus and copper goes to copper 2 plus, right? So electrons flow from the zinc rod to the copper rod, and the voltmeter registers plus 1.1 volt when the switch is first closed. So that means this is a spontaneous reaction. As soon as you connect the anode to the cathode, electrical energy flows. Okay. Right. So now you know what's a voltaic cell, you know what's a galvanic cell, and the 2 parts are connected by the salt bridge. Sometimes they may ask you for the function of the salt bridge. You know what it does? It basically connects the circuit and it maintains charge balance of the electrolytes. Because I told you in this first picture what happens. Zn2 plus, you got a lot of Zn2 plus. So you can see in the salt bridge, we generally make it out of KCl or NH4Cl, right? But the negative ions are neutralizing a high concentration of plus charges. And on the right-hand electrode, the plus charges, because copper is getting oxidized and we're losing copper, you've got to release K plus to maintain charge balance or charge neutrality. Okay, right. What would happen if no salt bridge? If only a wire and a few electrons pass, right? But then current stops. The right hand becomes because of the transfer of electrons into the left hand becomes positive. right? So electrons leave. This would prevent any further transfer of electrons. Adding a Sol bridge allows the two half reactions to lose their excess charge and permit more electrons to flow. You see that? What we're saying there is that if we don't have a Sol bridge, the Zn2 plus will become a high concentration and eventually electrons will stop flowing, right? And basically, you can see on the right-hand side, the same thing will happen. All right. Now, how does a voltaic cell work? Right. So you saw we put a light bulb and we basically, why do the electrons flow in the direction shown? What is the driving force? So now I told you how a voltaic cell works. You know the composition of a voltaic cell. You know how to write the two half reactions. Now let me show you why the electrons flow in the direction shown and what is the driving force. Right. So spontaneous reactions occurs due to different abilities of metals to give up their electrons. Right. So some metals, you know, they like to give off their electrons. You know, like people in life, some people are very stingy. They don't like to give off. We call them Scrooges. They don't like to give anything. They're very Scroogish. I wonder if there's such a word as Scroogish. And some metals, right? And we can measure that potential where metals want to give off, right? Like group 1 metals, they oxidize very easily, right? They like to give off electrons very easily. That's why if you take sodium and you add it to water, it's very reactive because it likes to form Na+, right? Anybody knows why? Anybody knows why Na likes to form Na+ very, very quickly? You see, when you learn something, it's nice to know why, right? And this comes in with your bonding, you know, your bonding knowledge. So I'll tell you quickly, but if you don't understand it quite readily, now remember, sodium has an atomic number of 11. I'm going to call out its electronic configuration, right? 1s2, 2s2, 2p6, 3s1, right? Now you see that's 11 electrons because in a neutral atom, sodium has 11 protons, so it will have 11 electrons. So I'm going to call its electronic configuration again. 1s2, 2s2, 2p6, 3s1. So 2 plus 2 is 4 plus 6 is 10 plus 1 is 11. You can go and check it out later. Now, you see that one electron, that 3s1, right? Now, if it gives off that electron, it then becomes 1s2, 2s2, and a 2p6. And you know what that electronic configuration, 1s2, 2s2, 2p6, does anybody have a periodic table or can tell me quickly? That's the electronic configuration for neon. And neon is a group 8 noble gas. So the Na+, so when Na becomes Na+, it becomes like a noble gas. It becomes stable. And it's S and the P. So the 2s2 and the 2p6 becomes a completely filled orbitals. And it becomes stable, right? But now we're talking about voltaic cells. But you see how important it is to understand, right, why these things happen. So spontaneous reactions occur due to different abilities of metals to give up their electrons and ability of electrons to flow through the circuit. Now you saw here, if we put these two metals together, zinc is very happy to give off its electrons. But how do we know that? I'll tell you just now. So just pay attention. Electrons flow from the anode to the cathode because of a difference in electrical potential energy. So it is higher in anode than in the cathode, right? So the difference in potential energy per electrical charge between the two electrodes is measured in volts, right? So you know 1 volt is 1 joule per coulomb. That means electrical energy can do work and is proportional to the difference in electrical potential between the two electrodes. So we're telling you that the potential between these two is that zinc can give off more electrons than copper, and the potential for it to flow is 1.1 volt, or that work that it's doing is 1.1 joules per coulomb of charge. So for every coulomb of charge that's going, every electron that's going across, it's doing work, right? It's like this. There's a ferry traveling from Dover in London to France. Every ferry is carrying 100 passengers. So every electron, and it's doing work, it's carrying people across. So these electrons, you can see them, every electron that's going across is doing work. Okay, so that's how we measure, and that's what we call a potential difference, or difference in potential energy, right? Which we measure as the cell potential. So the difference is measured with a voltmeter, and the reading is known as the EMF, or the E cell, right? So you know it's the pull or the driving force of electrons. That means how easy do these electrons move from the anode to the cathode? So now let's think about it. You know, we have these batteries that go into so first we used to have these torch batteries. And if we put a torch battery, the torch will light up, right? Now, if you take the torch battery and you go and connect your the battery of a car, it will not start, because that battery is not doing that amount of electrical work. So that battery is only doing about maybe, 1.5 volts. To start your car, we need just over 12 volts. So you need 12 times more of that battery to do that work. All right. So that's the difference. So cell potential, a galvanic cell or a voltaic cell, like we're showing you here, is always great. The E cell must always be greater than 0. And then we say the cell reaction is spontaneous. That means as soon as you connect it in the external circuit, a reaction will take place. What is that reaction? Zinc gets oxidized, copper gets reduced. More positive E cell, more work, right? More work cell can do, right? So that means more work can be done. And the further the reaction proceeds to the right as written. So that means the higher or the more positive the E cell, right? That means that cell can do more work. So remember that. Now, here's what we're going to talk about. So now we measure what we call a standard reduction potential of the two electrodes, right? So we measure the standard reduction potential of the two electrodes. So zinc metal basically has a standard reduction potential. Remember I told you about the potential difference, and copper also has a potential. So there's a value, and I'm going to show you that value. So zinc has more potential to give off electrons than copper, right? So we call this standard cell potential. So what is the standard cell potential? So a cell potential is measured under standard state conditions. So when we do a reaction under 298 Kelvin, 1 atmosphere of gas, and the solutions are 1 molar, okay? And if we have pure solids, we call that standard conditions. So if we have any other pressure, if we have any other temperature, then we don't call that standard conditions. We call that non-standard conditions. So whenever you see that E superscript 0, you know, E naught, we call it E naught. So that will tell, there's it here in red, the E naught, E ox naught, E reduction naught. That means we measured that under standard conditions. So 298 Kelvin, you know, it's basically 25 degrees C, right? 1 atmosphere of the pressure for gases. And if you're using solutions, we prepare a 1 molar solution, right? So whenever you see under standard conditions, that means we're controlling that condition and we know exactly what the conditions are, right? So we write this equation and we show this E cell and we put the superscript naught at the top. So whenever you see that naught, you know it's at 298 Kelvin, 1 atmosphere, and 1 molar, right? And we're using pure solids. Okay, so that's what we say. Someone is asking a question here. With respect to cell notation and cell diagrams, your cathode is always on the right. Okay, is okay, Ashwin? Oh, great, thank you.
I'm just confirming that.
Yeah, no, great, thanks. That helps a lot. I thought it was a student question. So Mr. Manival is also helping, and he's giving some good information. So you can see, as read what he's writing, because that's also helping what we're doing. Right, so you can see the E0 cell basically is at standard conditions. And now we have this equation EOX plus E0 reduction. But you know, we can also do it as E reduction minus E oxidation. So if you do it, it'll come to the same value of the E cell. But if you used to using this, then always just do E0 for the ox plus E0 for the reduction. Now, where do we get this E0 ox and E0 reduction? Right? Let me show you. Right. Okay, I'm not going to go through the standard hydrogen electrode, but what I'm going to tell you is that we have a selected standard electrode potential, right? So you remember I told you that we have different metals have different potentials to give off electrons. Now this standard electrode potentials has been measured for you. So this has been done in a laboratory, right? So let's look for copper. There's copper here. Can you see copper plus 2 electrons going to plus 0.3 volts? And let's look for zinc, right? Where's zinc? Maybe it's at the bottom here. Okay, jeez. Okay, they didn't put zinc here, but I know what the E0 value of zinc is. So let's just look at copper, right? Now, copper has a standard reduction potential. That means if I write it as a reduction potential of copper 2 plus 2 electrons going to copper, it's got an E0. When we measure that E0, it gives us a value of plus 0.3 volts. So the more positive a standard reduction potential is, it means it's very stingy, doesn't like to give off electrons. Okay? Now, let's look at something that's more negative. So can you see iron here? Iron, right? So iron, if you look at the reduction potential of iron, it's negative 0.44. So whenever you see a standard reduction potential, which is negative, it means that metal likes to give off electrons. So, which means Fe likes to give off electrons to become Fe2 plus. So that means, and I'll tell you a way of remembering it. Remember when I showed you zinc and I told you zinc has a negative charge on it. So you can just remember it like that when something is more negative. But also remember it's a relative term, because copper is more negative than oxygen. Or you can see here Fe2 plus. So can you see plus 0.34 is more negative than plus 0.77, if you understand what I'm saying. All right. So, and then also you can see negative 2.71, right, is more, or you can say plus 0.44 is more positive than negative 2.71. So it's a relative term. It's not in its literal sense that you'll have a positive and negative. You can have two positive values and one is more positive and one is negative. And you can have two negative values and one is more negative and one is less negative, or one is more positive than the other. But let's concentrate on copper and zinc for now. For some reason, this is a silly standard electrode potential table because they didn't put zinc. But if we had zinc here, and if we wrote Zn2 plus 2 electrons, it's got a value of negative 0.763 volts. Can you see? I remember that quite well, right? So copper is plus 0.3 volts and zinc is negative 0.763 volts. So it's telling me that zinc likes to give off electrons. So now you understand how we can work out the potential of an anode or a cathode. So when you look at the standard electrode potential, you will know which is going to get oxidized and which is going to get reduced. So let me give you an example here. Let's take silver, Ag plus E going to silver, which is plus 0.8 volts. And let's take iron, right? Fe plus 2 plus. That means if you look at Ag plus electron, it's positive. And if you look at Fe2 plus 2 electrons, that's negative. It means that the silver will be, right? Your silver electrode will be the cathode, and the iron will be the anode. Means that the iron likes to go in the reverse direction to get oxidized, and silver likes to get reduced. So you can make a note of this. The more positive the E naught value, right, it undergoes reduction. And the more negative the E naught value, that particular electrode undergoes oxidation. And if you remember that, you got no problems, then you know exactly which is the RHE, which is the LHE, and you can write down the two half reactions and the overall balanced equation. And then you simply calculate the E naught, where it's E ox minus plus E reduction. So for example, here I'm going to go through the calculation, right? So here at the bottom it says more positive E naught half cell, more readily half reaction occurs, right? So we remember that, right? For a spontaneous reaction, the E cell and this half cell with the more positive standard reduction potential is the cathode, right? It's, see what it's saying? A more positive standard reduction potential is the cathode. So like I told you here, copper has got a plus 0.3 volt standard electrode potential. It's basically the cathode. Zinc has a negative electrode. It is the anode. Okay, so you can see basically how we can work out standard EMF values. Right, now let's look at the calculation. Okay, let's look at the calculation. E naught values, right, are for reduction half reaction, and the sign must be reversed when used for an oxidation half reaction. What does this mean? Let me take you back to our equation. Remember, I wrote an equation here. There we go. So remember, we're still dealing with E naught now. That means at standard conditions, right? It simply means we're working at 25 degrees Celsius, 1 atmosphere of pressure, and our solutions are 1 molar. So E naught cell is equal to E ox plus E naught reduction, right? So on this table here, it's only giving us reduction. So if we were going to, and like say, for example, we basically working with Ag plus electron going to Ag solid, and say Fe2 plus 2 electrons going to Fe solid, which is negative 0.44. Now, if we were calculating it based on those two, right, we know that the cathode, right, is basically silver. So, and the anode is iron. But you can see here we're writing it as a reduction. So we have to reverse this as a oxidation. So the sign will also change to plus 0.44 when we are applying that equation. Now let me show you what I'm saying. Right. So and also if we are balancing, changing stoichiometric coefficients does not change the value of an E naught. That means if we have to multiply to take care of electron balance, we still keep the E naught the same. We don't change the E naught. We call them intensive potentials, right? They're independent of the number of the stoichiometric coefficient. So here's an example, right? Here's an example. Determine the cell reaction and the cell potential for a cell based on the following half reactions. Now, you can see you got your two half reactions. So let's go to our table quickly and let's see what the values are, right? So, oh, there's lithium right at the bottom. It's negative. That tells you that lithium likes to be oxidized. And let's look at silver. Silver is more positive and it likes to be reduced. So immediately you know what is your anode, what is your cathode. So your cathode is going to be lithium, your anode is going to be silver, right? And you know what your two half. So you see how easy it is, okay? So, and basically then you're gonna now, so that means the half reactions will be lithium is going to be oxidized to so that we reverse the first reaction, because that's now going to be the oxidation, and lithium, and that is going to stay as is. So E naught cell will be, right, E naught cell, let's go to our table here, is going to be, we're going to reverse the sign on this, 3.05 plus 0.8. So that's going to be 3.85 volts, right? So the E naught for this particular cell is going to be 3.85 volts. Okay, does everybody understand that? And is everybody, does it make sense to you? Can I get a thumbs up to say that it makes sense to you? Right. So now you know what is, and you know what, guys, you're going through we're going through load shedding now, right? Thank you for that. We're going through load shedding. If you think about, hey, let's try and create a cell that can, run our lights in our house. Let's get an anode and a cathode, which can do this for us, right? So here you're using your electrochemical knowledge. All right, so here's another example. A cell can be prepared from copper and tin. What is the E naught cell for the cell that forms the following half reactions, right? Can you please do this quickly and just simply post your, it's so easy because now I told you, you got the standard half reactions, right? Oh, here's an example now. You have to decide which is more positive and which is more positive and which is negative. So then you'll realize which is the anode and which is the cathode. Can you please do that quickly, right? Okay, so let me just help you first. So which is obviously more positive? More positive is obviously copper, right? Can you see? Plus 0.34 volts. So the tin is less positive, right? So you'll know obviously now the copper is going to be your anode, the cathode, and your tin 2 plus is going to be the anode. So please do this for me. Calculate the E naught at standard conditions and post it on the chat here quickly. Let's see what your values are. Let's see if it's whether it agrees with A, B, C, D, E. Quickly. Won't take you long. You can do it. You can actually do it in your memory, in your minds. Come on, I worked it out already. I'm sure you guys should work it out. Right, so I'm saying to you that E naught cell is your E naught plus, right? So it's E. So copper is going to be your cathode and tin is going to be your anode. So if you go to your E naught cell, you'll use this equation that we used at the top here. I'm just going quickly. E naught cell is equal to E naught ox plus E naught reduction. Put that in quickly. I'll just put this back on here. Right. Anybody got that answer? What is the E naught cell for this reaction? Okay, I'll give you a few minutes. I know I'm rushing you, but I'll give you a few minutes. You can just put it onto your chat, the answer. Even if it's wrong, don't be, you know what? If you get it wrong, it's better because then I'll explain to you and you try it. But if you get it right, it also means that you're good because you understand what's happening, right? So in your exams, they'll ask you to calculate this. They'll give you a problem like this. Anybody worked it out as yet? Shouldn't take you so long. You should have worked it out. Oh, good. I see some B. Galaxy J6. Let's see. Good. Anybody else? Come on, guys. The more you engage, the better it is. Challenge yourself and you'll be more confident as well. Don't be scared. This is a learning platform. It's important for you to learn. And don't be scared of failing, because failing is something that spurs you to try again. You only fail if you stop trying, right? Remember that. You only fail if you stop trying. BB, okay, Santuri worked it out. Good, right? Okay, so I'm sure the others you may have worked it out as well. So it's obviously B plus 0.21 volts. And the questions that can ask you, is it a spontaneous reaction? Yes. Will electrons flow in the external circuit? Yes, etc., etc. So this is the E naught, and this is working from standard reduction potentials. You will not get it wrong, okay? And you will work this out. Ashwin, can we just take a break, and then we can probably come back and I'll do the Nernst equation and doing it at non-standard conditions.
Okay, we can do that. But Dr. Bissessur, one thing.
Sure.
Our equation we're using, the E cell is the E ox plus the E red.
Yeah.
Yeah, so in the students' texts, I've noticed in the exam papers and stuff, we have the equation E cell is the E cathode minus the E anode.
You'll get you'll get the same answer.
Yeah, if you could just explain to them why one has the negative, why one has a positive, how one is taking the shift of the sign into account. They may be confused.
So yeah, sure. Okay, when we come back, I'll explain how we. Okay, thank you. All right, I'll do that. When I come back, I'll explain. But it's exactly the same thing, and it comes to the same answer. Okay, so it's now 7 o'clock on the button. We'll pause there for 5 minutes. Ashwin, is that okay?
Yeah, that's perfect.
Okay. Okay, I'll be back in 5 minutes.
Thank you.
Okay, welcome back. Right. Let's continue, guys. Ashwin, are you back with us? We'll just wait for. Right. So you can see, guys, when you look at a particular problem, you've got to see what's given. You've got to know the rules of electrochemistry. You got to know what the information. So like you saw now, I've shown you a standard reduction potential, right? And how to use that reduction potential to understand whether a particular compound will be subject to oxidation or whether a particular compound will be subject to reduction, right? So you saw how now we can identify which, but so now you saw zinc and copper. We know the standard electrode potentials, and we can use that to understand. Okay, now Mr. Manival told you that we did our calculations based on this. E naught cell is equal to E naught ox plus E reduction, right? So now there is another way that you, and I'm sure you are used to this calculation where we say E naught cell is equal to E reduction minus E RHE minus E LHE, which means E naught, the reduction, the cathode at which reduction takes place, and E naught where oxidation takes place, right? So when you do that, right, so we can calculate E naught cell by using that is equal to E, right, RHE minus E naught LHE. Right, so let's do that in this particular equation, right? So in this particular example, we're going to do here. So we're going to do E naught cell is equal to ERHE, the right-hand electrode. So that's going, right? And so that's going to be E naught RHE minus E naught LHE. Okay. So in that case, what are you going to get? Right. So let's work it out again and let's see what we got. Right. So in the first case, we are saying E naught cell is equal to E naught ox plus E naught reduction. E naught oxidation minus E naught reduction, right? E naught oxidation. So here we said E naught oxidation was the tin, right? So we had to reverse the sign, right? Plus E naught reduction, right? Which means the copper was more positive and it underwent reduction. So if we reverse the sign, right, then we got minus 0.13 plus 0.34, we got plus 0.21 volts. Okay. And then we said we're going to get E naught of your cell is equal to E naught RHE, the right-hand electrode, minus the left-hand electrode. So that's going to be E naught 0.34 volts minus 0.13 volts. Now, in that case, we simply take the reduction potential. So it's going to be E naught 0.34 volts, which is the RHE, minus E naught, which is the LHE, and you also get 0.21 volts as your answer. Okay. Does everybody understand that? So you can use it two ways. You come to the same answer. Can you give me a thumbs up and you understand that? Okay, so you'll come to exactly. Okay, Nomzamo, that's great, right? So that's good. You understand that. Right, cool. Righto. Now, and here's an example. Let's do this example as well and see how we can do that, right? So what is the E0 cell for the cell represented by the combination of the following half reactions? Okay, so here you can see the more positive E0 value is the mercury 2, right, getting reduced. So that reaction will stay as is. And here you can see the more negative, which means the chromium gets oxidized. So chromium solid gets oxidized to chromium 3 plus. So you know that the oxidation or the reducing agent is chromium because it gets oxidized, and the oxidizing agent, or what gets reduced, is the Hg2 plus gets reduced to Hg1. Now you see this Hg2 plus, it's actually a dimer of Hg plus. We don't get Hg plus existing as a single species, right? So it dimerizes, and we always represent Hg plus as Hg subscript 2 plus. That means it's actually Hg plus dash Hg plus. There's two Hg pluses that are bonded to each other, dimerized. Okay. And can somebody work that answer out for me quickly? So we can do that quickly. So it's going to be E0 cell is equal to E right-hand electrode, which is minus 0.94 minus into minus 0.74. Don't forget now, E0 right-hand electrode. So the right-hand electrode is the Hg2 plus. So that's going to be 0.92 volts minus, open brackets, minus 0.74. So that's going to be 1.66 volts, which your answer will be D.
D.
Thank you. Thank you. Yes, please shout it out. Right. So you see how easy it is to work out these cells. It's not difficult at all. Okay. And I'm glad you guys are enjoying it. And you must enjoy what you're doing as well. You mustn't fight with chemistry. It's a very interesting subject where you can understand now what it means. And you can see it's a spontaneous reaction. If you connect these, you're going to get a flow of electrons going, right? And you can see now with this here, select the strongest oxidizing agent amongst the following. Okay, so let's look at these reduction potentials. Okay, I said, now you see all of them are negative, right? So we've got to find out which is most negative and which is most positive. So we said, if something is positive, if something is more positive, it likes to get reduced. So it's an oxidizing agent. Now let's get the terminology right here. Wait, whenever you get lost, go back to zinc and copper. And always remember, copper was positive, so it got reduced. Zinc was negative, it got oxidized. So the zinc anode was it was a reducing agent, it got oxidized. So let's look for the most negative compound here, right? Or let's look for the most positive, right? Because if it's an oxidizing agent, it gets reduced. So let's look for the most positive. And the most positive one is the cobalt. Can you see here? Although it's a negative, somebody gave me the answer. E. Well done, Santuri. Well done. Yeah. So cobalt is going to be the strongest oxidizing agent because it's most positive relative to the others. You see that? Great stuff, right? The others get it? So it's which is the strongest oxidizing agent will be cobalt because it's the most positive. And if I ask you which is the strongest reducing agent, it will be chromium because it's the most negative. Right. So now we understanding all of these things. Right. Now here's an example, right? Here's an example, what you'll see. Now you know what's a galvanic cell, right? It's a voltaic cell. If you connect the two cells together, you'll get something happening at the anode, something happening at the cathode. So you know that oxidation takes place at the anode and reduction takes place at the cathode. And if you connect the external flow, you'll get electrons. Then you need a salt bridge. So you got this very good memory now what you have. So you see you've got an iron electrode in a 1 molar solution. You've got a silver electrode in a 1 molar solution. And calculate the standard. Whenever you see this word standard, you're going to put E superscript naught. So obviously it's 25 degrees, it's 298 Kelvin. And when you see 1 molar, you know it's standard condition. Sometimes these are not gases, so they won't give you the pressure. So calculate the standard, right? So that's easy because now we have to write out, right? So we have to write out so a galvanic cell, calculate the E naught. So we now have to find out what undergoes oxidation and what undergoes reduction. So if you look at an iron electrode, right? So the iron electrode and a silver electrode. So let's go to a standard, let's go to our reduction table. So when you look at the reduction table, right? Here's iron here, there's iron. It's negative 0.44 volts, right? And the other one was silver, isn't it? Right? Silver is plus 0.8, right? So I'm coming back to this example. So iron, you saw there, the reduction was negative 0.44 volts and silver was positive 0.88 volts. So the iron is gonna undergo oxidation. So Fe is going to give off electrons and silver is going to, so the AgNO3, so Ag plus the electron is going to go to Ag and the iron is undergoing oxidation, right? So there, what we're going to do is we're going to go back to the standard electrode potential table, excuse me. And so we were dealing with silver. So I told you silver is going to undergo reduction. So if we use E naught is equal to E right-hand electrode, that's E, that's plus 0.8 minus E naught left-hand electrode, which is minus into minus 0.44. So it's going to be 1.24 volts, right? So everybody with me, right? So in this example here, you're going to, if they tell you this, look for the standard reduction potential for iron and look for the standard reduction potential for silver. Then you'll know that Ag plus electron is going to go to Ag and Fe, because you can see NO3 is -2, there's going to be -2, so this is Fe2 plus. You must know your oxidation states. So Fe is going to give off 2 electrons, right? So the anode is the iron electrode and the cathode is the silver electrode. Then you know that silver is going to now deposit on the silver electrode, right? And you can calculate the standard EMF of this particular cell at 25 degrees Celsius. Is the following reaction spontaneous as written, right? Right? If not, write the equation for the spontaneous reaction and calculate the E naught of the cell. In other words, what they're saying is, will iron 2 plus, right, become reduced and become oxidized, right? Is the following reaction spontaneous as written? So let's go to the standard reduction table. And all you have to do there, you can see iron 2, right, getting oxidized to iron 3. And here at the bottom, iron going to iron 2, right? So that's iron, it's negative 0.44 volts go to iron 2. But for iron 2 to go to iron 3, it's very hard. Can you see that? So if we go back, right, to what they're asking here in this equation, right? So iron 2, you saw, to go to iron 3 is not spontaneous because it has a positive E0 value, right? If not, write the equation for the spontaneous reaction and calculate the E0 cell. So iron goes to iron 2 plus, right? So let's not worry too much. I don't think they'll really ask you about, questions like these. They'll just ask you the general questions. But you can see how to do this particular question, right? So you can see iron 2, basically, it's more the iron going to iron 2 rather than iron 2 going to iron and iron 3, right? So, right. A voltaic cell houses the reaction between aqueous bromine and zinc metal. So there's another reaction. They give you the E0 cell and calculate E0 of the bromine, right? Now, I want you to look at this example here. Previously, we gave you the 2 species and we told you to calculate the E0. Now they gave you the E0 of the cell and they want you to calculate the E0 of bromine. That means the bromine half cell. And they gave you the E0 of the zinc. There we go. I was right? The standard reduction potential for zinc. Now, what do we do here? So first we've got to look at zinc is getting oxidized to Zn2 plus. So you know, whenever it's negative, it gets oxidized. So this reaction tells you that zinc is the reducing agent, it got oxidized. That means bromine got reduced. It's the oxidizing agent. So you know that this here is the anode, right? It's the anode or the left-hand electrode. So remember we said E0 is equal to E right-hand electrode minus E left-hand electrode. So you're going to write 1,83 volts is equal to E right-hand electrode, right? Minus into minus 0,7, or you can say E0 cell, right, is equal to E0 right-hand electrode minus E0 left-hand electrode. That is equal to the right-hand electrode is the bromine and the E left-hand electrode is the zinc. So you know it's going to be 1,83 minus the E right-hand electrode minus into minus 0,76 volts. And then you make the E0 for bromine and you get the answer. So in this example, they just want you to find out, so which is the left-hand electrode, which is the right-hand electrode, and you can easily see that whenever you see a negative, that's going to be the left-hand electrode, which is the anode. Okay, and you can do your calculation. Right, now I want you to pay attention for the shorthand notation or the line notation. Can I just have a thumbs up that you know about the shorthand notation and you've done it? Somebody's, yeah, okay. 1.07, yes, Santuri, well done. That's good. That's the answer. Great. Right, now, remember I showed you a picture of the setup. So this is an illustration, right? So now when we write the shorthand notation, right, or the line notation, we write it like this. So you can see there's the zinc solid and there's the zinc electrodes in this diagram. The Zn2 plus is the solution. So we write aqueous for solution. The double lines is the salt bridge. Then there's the copper 2 plus aqueous, which is the copper 2 plus in solution. And the copper solid is the electrode. And that's all you write. If you know the concentration of the zinc, just say they give you the concentration. Instead of writing aqueous, you can just put 0.1 molar or 0.1 molar as the concentration. Okay, so this is the key parts, and you can see how we write it. Okay. A voltaic cell prepared using aluminium and nickel has the the other thing I must tell you, obviously, you can see here's the zinc, which is the left-hand electrode, and copper is the right-hand electrode. So like, I think somebody asked me earlier on, will it always be like that? Yes. So as you see the physical setup of the cell, the line notation shows you exactly. So copper is the right-hand electrode, zinc is the left-hand electrode. Okay. So if they give you this diagram, then you can write the line structure. And if they give you the line structure, then you can draw the actual structure of that. You want to know the answer for the bromine cell. Okay, can you work it out for me? So just write 1.83 is equal to E right-hand electrode minus E left-hand electrode. So 1,83 is equal to E right-hand electrode minus into minus 0,76. So that's going to be E naught of the right-hand electrode is going to be 1,83 minus 0,76 volts. Okay. And I think Santuri worked that out to be 1,07. I don't have a calculator on me, but if you guys can just work that out. So it's going to be 1.83 minus 0,76 volts. Okay. Yeah, it's about, yeah, it's right. It's 1,07. That's correct. 1,07 volts. You got that? Yeah, that's right, Nomzamo. That's right. Great. Okay. Now, you saw the notation, and here's an example. A voltaic cell prepared using aluminium and nickel has the following cell notation. Which of the following reactions occurs at the anode? Okay. So obviously, as it's written, the left-hand side is the anode and the right-hand side is the cathode. So obviously, oxidation takes place at the anode and reduction takes place at the cathode, right? So which reaction takes place at the anode? Quickly post your answers. Come on, you should get that quickly. Which reaction takes place at the anode? Quickly, quickly, quickly. Just post A, B, or C. No, no. Why are you saying C? Which reaction takes place at the, according to this cell? I'm telling you again, here's aluminium, which is the left-hand electrode. It's the anode. The right-hand electrode is the cathode. Come on, think again. So the answer should be? Okay, right, that's better. Okay, great. A is the answer. Right, so aluminium goes to aluminium 3 plus 3 electrons. Right, and then you can see the reduction reaction will be D, Ni2 plus 2 electrons. So those are writing the 2 half reactions, right? And then you write, then you've got to now balance the electrons. So you'll multiply A by 2 and D by 3, and you'll write the overall equation, right? Now, there we go. A voltaic cell is prepared using aluminium and nickel and has the following cell notation. Which of the following represents correctly the balanced spontaneous reaction equation for the cell? I just gave you the answer just now. Okay, so what's the answer? The answer is overall balanced equation. So you got the 2 half reactions, right? You can see it there already. What's the answer for this here? Come on, you can see the balanced equation. So we said aluminium, right, is undergoing oxidation. So it's going to be answer to this. Aluminium undergoing oxidation, nickel undergoing reduction. So we have to balance the electrons. Your answer is going to be no. Okay, let's think about this. I said to you in this reaction here, it's the same thing, right, as that. So we said, which of the following occurs at the anode? It's that aluminium, right? Going to Al3 plus 3 electrons. D is the reduction, right? So now we want to write the overall equation. For the overall equation, we've got to get the balance right. So you're going to multiply Al, right, by 2, and you're going to multiply this by 3. So you got 2Al going to 2 Al3 plus 6 electrons, and you got 3Ni2 plus 6 electrons going to 3Ni. So the 6 electrons and the 6 electrons cancels, and you're going to get, I've given you the answer now.
Yeah, I think Dr. Bissessur's just dropped out because of internet. But we'll just give him 2 minutes. I'm sure he'll be back on. You had a question, Chamber?
Yes, I said, would you need to learn the standard electron table?
No, they give these to you in the exam.
Okay, thank you, sir.
So, You're talking about the values, right? You're talking about the half reactions and their values.
Oh, yes, sir.
Yeah, so the table of electropotentials, you find them in the back of textbooks. They're reference material. But there is one you'll have to know. That's the standard hydrogen electrode, right?
Okay.
Because it's the reference for everything else. 0. Okay? It's fair game to ask you that. But again, you'll find that on the table as well. Okay, if you have a question about mathematics, what I suggest to do is you send an email the question to the mathematics helpline, then I will forward that question to one of the tutors in maths, and they will be able to help you, right? They'll get back to you tomorrow, I'm sure. So here's the email addresses for the 3 subjects. You can take a photo and just send it on however you want to send it, right? What answer did you guys get for this? For this question we're doing now? Okay, so what answer did you guys get for this? You just post it in the chat. Somebody's asking if you're going to have more physics and chem meetings. This was supposed to be the last one, but we can arrange more. So if you send us emails, we will arrange around you, right? So we're going to run this program throughout the whole semester, throughout the whole year, until the final exam. So we're going to have weekly sessions with multiple sessions in the week. So there's going to be a lot of opportunity to do more tutorials. We'll communicate that with you as we proceed throughout the year. If you keep an eye on our website, the schedule will keep updating and you'll know. But if you've signed the register and I have your email address, I will email you, send you emails of the schedule so you'll be able to know when the sessions are. Okay, so when are your papers for chemistry? When is this paper 2? When are you guys writing? Just put it in the chat. You can just put the date in the chat. Okay, we have a 20th June. Anybody else? Okay, guys, you must know when you're writing the paper, right? If you tell me when we're writing the paper, then I'll know how to proceed with the session. If we have time, we can arrange another session next week. Okay, this is what I'm going to do, right? Some of you are sending email addresses. I can't copy them from your website. What I'm going to do is I'm going to send you a register link, okay? So please go to the register link and fill the register in and put your email address in so that I have a record of it. I won't be able to copy it off the chat. It doesn't allow. It's kind of like a safety feature. So I'm just going to send this. So if you go here, just give me 1 minute to copy it. Right, if you go there, you can fill the register, and when you fill the register, you can leave your email address and I'll send you schedules, right? But don't post your stuff on the chat. Don't post your email address, anything personal, right? Even if it's directly to me, don't do that. Okay, so that covers that. Okay, this is what we're going to do. We're gonna close up this this question today. I mean, what we were talking about now. The question that we were discussing now is this one. And then we're going to arrange a session for next week with Dr. Bissessur to do the Nernst equation. So basically, Dr. Bissessur was finished with this anyways. But let's quickly see your answers for this. Which answer is this here, guys? Just leave it in the chat. What did you guys get? Okay, so there's two things you got to get right here. Two things. The first thing is you've got to get the direction of the equation right, which means the right species have to be on the correct side. The second thing you got to get right is the stoichiometry, or the actual number of species in the equation. So if you look at this equation, remember we said the right hand side was the reduction and the left hand side was the oxidation. And so what you naturally will have is you'll have reduction, which is the gain of electrons, so the oxidation number will drop. You'll have the nickel 2 plus going to nickel 0, right? So nickel 2 plus going to nickel 0. That has to happen. And you'll have your aluminium being oxidized. So aluminium 0 going to aluminium 3 plus. Now, if you look at all your equations, if you look at the first one, you do have this here. Nickel 2 plus going nickel. Okay, so maybe it's A. If you look at B, you have that there. If you look at this one, right? You look at C, straight away you see something's wrong. Because when you look at C, suddenly the nickel is actually in reverse. That's not right. Nickel's on the right hand side. It should be undergoing reduction, but this nickel, so C is out. If you look at D, that can't be right, okay, because you see it's supposed to be undergoing reduction, but it's increasing its oxidation number. So C and D have to be ruled out. Now you're left with A and B. But now you've got a problem with A and B, because if you look at these reactions, you can see that the nickel is a 2 electron transfer and the aluminium is a 3 electron transfer. Now here's the thing, when you combine in half reactions, you have to combine them in such a way that the electrons are the same in both half reactions. Obviously, if a certain number of electrons are involved in the reduction, the same amount of electrons need to be involved in the oxidation. That's logic, that's common sense. So straight away A can't be true, because you can't have all of these guys with 1, 1, 1, 1 stoichiometric coefficient and have different number of electrons transferred and be happy about it. That's not working. But when you look at B, you can see, wait, hold on. If nickel is transferring 2 electrons and you times it by 3, you get 6 electrons. And if aluminium is transferring 3 electrons and you times it by 2, you get 6 electrons. So B is the correct answer, because B has the right direction, taking your anodes and cathode into account, but it also has the balanced, correct number of stoichiometric coefficients that satisfy the amount of electrons that should be transferred. So B is the answer. Does that make sense? Anybody have a question about that? Okay, let's leave it at that then, right? We'll stop the session here. I will be in communication with you about Dr. Bissessur's session for next week when we do Nernst equation, non-standard conditions, and then we'll take it. Any more sessions you want scheduled, just let me know, and we will work around scheduling them for you. Any questions? Any other questions? No questions? Okay, thank you for attending, guys. It's been a pleasure. Enjoy your weekend. Cheers, bye-bye.
Thank you, sir.
Bye.
Thank you for the lesson.
No problem.